Morning, everyone. This video will be about a material selection methodology laid out by Michael Ashby. Um, but before I get into that, I just want to apologize for the lateness of this video. It's been kind of a slow start to the week. All of the rain we got the last day or two hasn't helped. Had some water to help deal with. This material is meant to be helpful for review for the test and to help to put some of the material we've talked about in context and to fill in a little bit of how one might go about selecting a material. It is not a methodology that I would expect you to be able to execute based upon this video. It's more for context and exposure, and so don't stress about this on being on the midterm or anything. That's not going to happen. The Callister material will be the source for all of the midterm, and I've already posted a study sheet and an equation sheet for that exam. There's a set of notes that go with this video, and I'll be switching to them here in a minute. Those are already posted on Teams. So I'm going to go ahead and switch over and share the material selection notes. Okay, so like I said, this is derived from a book by Michael Ashby called Material Selection in Mechanical Design. I used the 3rd edition, and that source has a lot of useful figures, and I'm going to try to zoom in. Hopefully that zooms in on the video. Not sure. I'm going to try to zoom in because these diagrams have a lot of detail that is difficult, to see when they're small. One of the reasons why we need a methodology for selecting a material is because, throughout, especially the 20th century, the number and variety of materials available to designers has grown rapidly. This figure here, I think, is a nice one to put materials science kind of in the proper context. I talked about a little bit of this, in the introduction at the beginning of the course, in that materials have been around forever, right? There are natural materials that fall into all of the material classes that we typically think of. And as society has developed and technology has developed and industry has grown, we've shifted from natural materials to man-made materials, right? And that has come with great gains in material properties, consistency, controllability, optimization. And I think it's interesting to note here kind of the role of metals throughout history, right? You see here, I mentioned before how we have ages of history, especially kind of antiquity, right, named after metal working knowledge, right? So we have the copper, bronze, iron age. And iron really starts to take over, right? Say, for the last 1,000 years or so. You have your cast irons, then your steels. You get more fancy with the steels. Start to add alloying elements. This makes them more heat treatable. Also makes them stainless, right? So we kind of address that corrosion problem. Then in the mid 20th century, we have aluminum alloys, magnesium alloys, titanium. lighter, we have to figure out how to process and use the lighter elements, lighter alloys that gives us great gains in aerospace. But then alloys kind of hit a high, or metal usage hit a high point in the 60s, right? And since then we've seen their usage curtail in line with the growth of polymer systems, right? So you might use our my parents, when they were kids, right, they had a metal, their toy trucks were made out of metal, right? These days our kids play with plastic trucks. That's just kind of a silly example, but for areas where you don't need the metal strength and ductility, right, we've replaced that with polymers, and as we have developed the polymer technology, right, we have more specific polymer systems that are suitable for more and more applications. And so you start to get crossover between suitable materials, right? So I could make it out of a high temperature polymer, or maybe I pick a metal, right? And as all the different material classes grow and develop, and they start to overlap, and so you might have an application where you could conceivably choose one of a number of materials from widely varying material classes. And so the same thing has happened here with composites materials and ceramics, is whereas metals have kind of waned, and these materials have grown in importance and in capability, right? You see that shift occurring. And so if you add together, right, all of this growth in materials, we find that we have a great number of materials from which to choose, right? A number quoted by Ashby is more than 120,000 different materials to choose from. And so how do you go about choosing the right materials for your application? Oftentimes you can rely on past experience, previous testing, or previous generations of the same product. But if you're starting from scratch with a brand new design, you might have your your design space very, very broad, very open, and so then you could say, well, I'm going to think out of the box, and maybe I pick a material that I've never used before. But if you're looking at 120 different choices, how do you make that choice? And so it's helpful to have a systematic procedure, which is what the latter half of this talk will outline and illustrate with a couple of examples. And so when you're making a material selection, that is guided by other factors, right? First of all is the function. So, what material you pick is going to be dependent upon what the thing you're making out of that material is supposed to do. And so the function is very important, but it's also linked with the shape of the material, the process that you're going to use to make the material, but then also to make the part, right? Or is this a cast part or a forging? And so, right, when you pick the material, as we saw in our previous lessons, is that not all material classes can be formed via the same processes or attain the same shapes. So you can't choose one or another of any of these categories independently, right? The function of a material, the loads that it needs to carry, the thermal conductivity, all of that is going to be dictated and dictate the shape and the process and the material, right? And so when you're choosing a material, that is going to limit these other categories, and they are also going to limit the choice of the material. So all need to be considered at the same time. And if you specify one, then you're going to be restricting your choices in many of the others, right? And we'll see this in the material selection methodology. The first part of this talk will basically look at some aggregated data on different material properties, which will hopefully help to be somewhat of a review about the various materials classes. But here, by way of review and synthesis of these ideas, the big takeaway is in comparing different classes of materials against one another in regards to various properties or combinations of properties. And in our previous lessons, we talked about metals, ceramics, and polymers, and then composites. Here, Ashby is a little more specific in that he separates ceramics into ceramics and glasses. So you'd have sort of your more crystalline ceramics and then your amorphous ceramics. And then and then also splits out polymers into polymers and elastomers, right? So remember, elastomers are characterized by much larger degrees of elastic deformation due to cross-linking, and then the hybrids is what he uses to describe the composites that we covered. Okay, so now we're going to look at a lot of the material properties that Ashby cites and that he provides material data on. And a lot of these should look familiar from what we covered in Callister. The general properties, right? We have density, we have price, right? We didn't really talk about price up to this point, but when you're making material selection, you have a price point for what you want to sell your final product at. And if you pick a really expensive material, right, then you make it harder to make a profit if that's what you're interested in, right? From a government standpoint, price is not always the controlling factor, right? You may be able to pay more to get more performance, and that might be necessary. Probably the biggest category of material properties are mechanical material properties, right? We saw that we focused on mechanical properties of metals. That was our first introduction to mechanical properties in this course. And there's a lot of different ways to describe the mechanical properties of a material, right? Remember, we have the elastic modulus, that's the slope of the stress-strain curve in the elastic region. The yield strength, right? That's where you transition from elastic to plastic deformation. Your ultimate yield strength is the highest strength that you attain after a good amount of cold working and deformation. Remember, as I deform the material, I'm creating more dislocations, which is making it stronger and more brittle until ultimately it has necked to the point where I start to see a decrease in the applied stress. Right? Remember, we corrected for this in our homeworks, that it still continues to get stronger until you get fractured, but because I'm not adjusting the area, right, it appears that I have a reduction in stress, but what I really have is a reduction in cross-sectional area there. And so this is a typical tensile strength or tensile test for a metal, but we also have mechanical properties that you don't necessarily derive from a stress-strain curve, such as fatigue life, fracture toughness, right? These are done with other testing, fatigue testing, where you would apply a cyclic load for many cycles until failure. Fracture toughness, where you would apply an impact loading, right, where you would apply a lot of force in a very short amount of time to a pre-notched sample, and then measure how much energy it takes to fracture that material. The one we didn't really cover in this course is loss coefficient. Right, this would be the ability to dampen out vibrations, and so we have a lot of different mechanical properties, which is indicative of the material need for a lot of different applications. Most of the time, we are building something that will carry a load of some type, and so we want to know that material, that object, that can carry that load, and then characterize how long it can carry it and under what conditions. So stress strain mechanical properties is important for metals, obviously, but also for the polymers and ceramic materials as well. But the nature of the mechanical behavior varies significantly. We see this in polymers, that there's a wide range of mechanical behavior, ranging from very brittle polymers to very what's the word? Ductile polymers, and everywhere in between, right? And so you have a wide range of ductilities in metals also, but polymers are distinguished by the fact that you can get a very drastic change in mechanical properties over a relatively narrow temperature difference. And so you can actually generate, all of these different stress strain curves from one polymer system just by changing the temperature, right? You see here that you get very brittle failures if your temperature is below the glass transition temperature, right? Which means that, you don't have enough energy in the material for those polymer chains to be able to move relative to one another. If I increase the temperature, right, then I switch that condition, and now they do, and so I get very large amounts of deformation. Let's see here. And then for ceramics, the stress strain curve, ceramic materials tend to have very steep, very high modulus, but very little amount of or no plastic deformation. And so a stress strain curve for a ceramic material might look something like this, where you have sudden failure, and in this case, I guess this is a compression test, you have successive failures as you have cracking propagating through the material. So in a compression test, you don't have one rupture. You have a series of them because you're compressing it rather than putting it under tension. Okay, and so we have talked a lot about mechanical properties. Didn't really touch on thermal properties except for, say, diffusion. But there's a lot of, from a design standpoint, there's a lot of thermal properties that are of interest. Right? I guess we did talk about melting point, glass transition temperature. But we have, maximum service temperatures, minimum service temperatures, thermal conductivity, specific heat, thermal expansion, and all of these are relevant to the operating environment of our application. Right? So I said a minute ago, especially in the case of polymers, is that there is a drastic change in mechanical properties with temperature, right? And so that is reflected in the glass transition temperature, maximum service temperature. And then you may, if your application depends on thermal conductivity, which one of our examples later in this talk does, right? You obviously will care about that. If you have a heat exchanger or a material that is being heated repeatedly, specific heat is of interest. If you have a union between two different materials, or you have one material inside of another one, thermal expansion coefficient is important. You want to make sure that you have the right tolerances so that you don't have stresses build up as one thing expands inside of another. And then, mechanical and thermal, as reflected here, are kind of probably the biggest two. And then other material properties kind of fall into what I think of as kind of niche um, applications or niche properties, in the sense that you care about them a lot for certain applications, but they're kind of secondary for many others, and those would be like electrical properties, optical properties, and then the environmental impact and environmental resistance. So, if you're building a semiconductor device, obviously you care quite a bit about resistivity and dielectric constant, breakdown potential, right? All these electrical properties. If you're building, say, a fiber, or have an application where you need to be able to see through the material, obviously optical properties would be of interest, and then in kind of, I think of this in tandem with cost, is you have sort of your economic and environmental considerations, right? Where you'd have cost to extract, cost both in energy or money or in carbon dioxide emitted. And then along the lines of corrosion that we talked about in our last chapter in Callister, that is going to be a consideration for materials as well, right? So you have corrosion or oxidation rates, and this is going to be heavily dependent upon the environment that you foresee your design seeing, right? So obviously you are going to be having a different approach to protecting against corrosion, right? If you're building something for use by the Navy, as opposed to the Army or scientific laboratory. And here at the bottom, we just have a couple of charts that display that kind of as a review for some of those other material properties. Right? Remember here, this would be fatigue testing. We have the stress amplitude as you cycle that stress, and your cycles to failure, right? So this would be probably a material like aluminum, where you don't see a hard fatigue limit, right? As you go up in cycles, it continues to go down, even though the rate of decrease will slow down. Here's thermal conductivity, would be the slope of the heat flux and temperature gradient. This is very similar to Fick's first law, except we're not looking at mass transfer, we're looking at heat transfer. But here, instead of having a concentration gradient, we have a temperature gradient, and then we have, instead of a mass flux, a heat flux, and then some sort of a constant that describes how quickly that heat flows through a certain cross-section, right? And that's analogous to that diffusion D constant that we talked about with diffusion. So thermal conductivity and diffusivity are very similar in concept. We also have electrical resistivity. This would be for an ohmic material, where we have V equals IR, right? So if we plot potential versus current, right, the slope of this would be the resistance. Okay, so we have measured, so these are the properties that we're interested in. And a lot of this data has been measured. But remember, right, with 120,000 different materials, if you were to display this data, say, in a big table, similar to what we had up here, right, it would be hard to get a sense for all of the data at once, right? And so Ashby has a lot of useful charts displaying the material properties amongst all the materials for specific material properties. For instance, here's an example for thermal conductivity. And so you see here, it shows a couple of things, right? First of all, you can see the range of the property, right? So, sort of ranges somewhere between 0.1 to, say, 500 watts per meter Kelvin, right? So you know right away that, okay, if I have a design that requires 10,000 watts per meter Kelvin conductivity, well, I'm not going to find it. So this kind of gives you a bound for where the material property exists, and then within that bound you can see where the various classes of material properties fall, right? So we already know that metals are good conductors both of heat and electricity, and so it's no surprise that we have high thermal conductivity from the metals, and some ceramics, right? But not sort of semiconductor ceramics, but that polymers and more industrial ceramic materials have relatively low thermal conductivity, right? So if you think about materials that insulation is made out of, right? It's polymers, it's glass, it's um, foam, those sorts of things, right? And if you say, okay, so what about heat sinks or radiators or wires? Right, those would be aluminum, magnesium, steel, copper, right? So that should make some sense with previous experience. And a chart like this is useful to see, like I said, the range of materials and where different materials fall. But it might actually, be not helpful. Let's say you had other constraints, right? Say not only, do you care about strength, but you also care about weight, right? And so you can plot, those properties at the same time to see the relationship between them. And Ashby provides a lot of figures that do this as well. For instance, here we have Young's modulus versus density, right? So this is sort of specific Young's modulus. And if you do this, right, you can see that instead of having a range where the materials fall, now you sort of have an area, right? So as a class of materials, for instance, foams are relatively weak, right? So they have low Young's modulus, but they're also relatively light. And so we see here at low values of, sort of this bottom left quadrant, we have your foams. And metals have the opposite characteristics, right? Where they're very strong, high Young's modulus, but very heavy. And so if we plot these classes of materials on the basis of Young's modulus versus density, right, we see a good separation of the different material classes. Right? And that's because, as we talked about, right, the bonding that exists between different material classes, it tends to be similar, right, which leads them to cluster at similar values for Young's modulus and density. So in addition to Young's modulus, right, you can also plot things in terms of strength. We talked about stress-strain curves in classes, previous lectures, and also above when we were talking about material properties that we care about. And so we have Young's modulus, which is the slope of the stress-strain curve. We also have the strength, which can vary for different material classes. For metals and polymers, we think about the yield strength, where we transition from elastic to plastic deformation. Ceramics, you have to define specific strength in terms of modulus of rupture. So this would be more related to a bending test, since for a typical ceramic material you can't do a tensile test. Elastomers, we care about the tear strength, and then composites, we would have sort of the ultimate strength or the tensile failure. And so you can build a plot of strength versus density with the caveat that the strength means different things for different material systems. And again, you see a separation of the different classes of materials, where you have high density, high strength metals, low density, low strength foams, and then you would have a range of strengths for composites, polymers, right, but a fairly narrow range of densities, kind of somewhere in between your foams and your metals, right? But here you can see strength versus density gives you, additional insight potentially. And then these next few charts are examples of different properties. So previously I showed modulus versus density and strength versus density, right? You might at first, this might not be the first thing that you would think of, but you can actually plot Young's modulus versus strength, right, and get rid of the density completely. And you say, well, why would you want to do that? It's not immediately intuitive. And the reason for this, it will become more, will make more sense later in these notes as we look at some examples. We're going to use this plot of Young's modulus versus strength to talk about design for springs. So it can be very useful in that context. You can also take that Young's modulus versus strength and look at it on a density basis, right? So if you divide both by the density, then you get specific modulus and specific strength, which again is helpful if you have a weight-sensitive application. And this highlights the difference here between specifically this specific modulus and specific strength highlights the difference between metals and composite materials, right? If you go back up and look at Young's modulus versus strength, you have your composites below your metals. If you look at it on a specific basis, right, you get an inversion here where your metals get bumped down because of their high density. And certain types, right, composites get a bump up, right? Heavier ones, not so much. Your GFRP, glass fiber reinforced polymer, right here, was significantly below the metals on a non-specific basis. But when you look at it specific, right, then it's kind of more parity with metals. And the carbon fiber reinforced polymers, the CFRPs, they really shine on a specific modulus and specific strength basis relative to the metals. You can also plot, right, along the lines of the mechanical properties here, getting a bit away from strictly tensile test stress strain curve data. Here we have fracture toughness versus elastic limit, and this really combines the properties that are related to fracture, and so what you have on here is all of the material classes, different major materials, and then we're looking at the process zone size. So this would be sort of like analogous to the grain size, or a crystalline region, size of a crystalline region. And as you get a larger grain, a larger crystalline region, this dotted line serves as the kind of the boundary between materials that would yield before they fracture, right? So as the fracture toughness increases and the elastic limit decreases, right, you're more likely to yield the material before it fractures. Conversely, if the elastic limit is very high and the fracture toughness is very low, right, this is getting into more ceramic materials, then we're going to get into a regime where we're going to fracture before we yield. And generally, it's more desirable to yield before you fracture. And so you can see here that as you change the process zone size, right? That would be like sort of the grain size. That's important because a lot of your materials will lie on one side or another depending upon this process zone size, and it kind of highlights the importance of processing and grain size to the ultimate mechanical properties, especially as related to fracture toughness. Um, yeah, okay, that's all I wanted to say about that. And again, as I did before, I kind of saved the more niche properties for last, but Ashby includes data on all these niche properties here. This chart shows the loss coefficient, so this is related to internal bonding and internal damping of a material. It's higher, right? The loss coefficient is higher for ductile materials because those vibrations are moving around the dislocations, and that absorbs energy, right, which will dampen out the vibrations in the material. If we look at, right, so materials with very high or very low loss coefficients, right, meaning that the vibrations are dampened out very slowly, right, these are good materials for, say, applications where you want low loss coefficients, for example, a bell, right? So if you look at bells are made out of bronze, right? Bronze is a copper alloy, and we see here that amongst metals, right, copper alloys have some of the lowest loss coefficients possible, right? And this is due to the pinning of the dislocations, right, in bronze due to that high, I believe, zinc content, right? So we have a lot of strain energy, a lot of the impurities, and remember that impurities and dislocations tend to co-locate, and moving a dislocation off of an impurity site requires a lot of energy, and so you don't get that dislocation movement, which means you don't get the dampening, and then these copper alloys have a low loss coefficient. And some ceramics can have, say, more common ones, concrete, brick, stone, not your more single crystalline, highly processed ceramics, tend to have a lot of tiny cracks, and these cracks rub against each other, which dampen out the vibrations. Likewise, polymer systems tend to have much higher loss coefficients because the polymer chains slide relative to one another and absorb energy that way. For conductivity and resistivity, conductivity, remember, is the flow of heat through a material. Metals tend to have very high thermal conductivities because of the metallic bonding and the sea of conduction electrons that flow through the material very easily. Now these free electrons are available to conduct heat. They're also available to become part of a current, and so metals are characterized by high thermal and electrical conductivity, and that's what we see here. The metals occupy this upper left quadrant, high thermal conductivity, and this chart is electrical resistivity. Resistivity is the inverse of conductivity, right? So high conductivity gives you low resistivity, and so here we see the metals occupying this region here, and then the polymers, foams, glasses have much lower conductivity, much higher resistivity, right? So we see those congregating here in the lower right. And we use this chart, we look at a design for a heat sink material in a few pages. Temperature-wise, we also care about max surface temperature. So here we have strength at high temperatures, right? This would be an important one for a lot of aerospace applications. and we see here that the polymers and foams have a relatively low maximum surface temperature, and it's really the metals. So the metals occupy a huge range of surface temperatures, right, all the way up to, say, 1,000 C or so, and a fairly healthy range of strengths. And so, um, depending upon the alloy and the heat treatment, right, you can get a wide range of surface temperatures and strength from metal systems. And so for high temperature applications, generally metals and to a certain degree ceramics are preferable. Okay, so lastly, we have cost. We've been focusing on the science in this course. We haven't really talked about cost, but in the real world, right, you probably start with cost, because if you can't afford it, well, it's hardly worth considering. And here we see that polymers, natural materials, are at the lower end of the cost curve. As you go up in cost, you typically have an increase in strength. So you have your metals up here, you have your semiconductor materials, your industrial ceramics occupying, right, the high strength, high cost quadrant. And you can think about, so strength versus cost, also modulus versus cost. In many ways, it tells a very similar story. And so I showed you a bunch of charts here. The point of these was, and Ashby uses them also, is to summarize a lot of information compactly, right? So 120,000 different materials in a lot of different subcategories, all displayed, and you can see the range for that particular material with regards to two or more properties simultaneously. So plotting the data this way, you can put a lot of information compactly and help you to zero in on certain categories of material very quickly. It also shows the range of properties that are possible, right? So you can see that if you're considering a certain material, that right off the bat, its range of, say, strength would be 50 to 80 megapascals, say, for instance, right? And so that can be helpful as kind of a quick estimate. Also, a combination of properties that are important to your application might give you insight that maybe you wouldn't intuitively have guessed before plotting the data that way. Also, all of these charts, we saw over and over again that the different classes of materials tend to cluster together. And this is due to the fact that the different classes are defined by having similar bonding behaviors, similar densities, lattice structure, crystalline nature, and so that is going to explain 90% of the variance. It's going to put them in a particular quadrant, perhaps, of a chart, and then even amongst the same type of alloy, right, you do have a little bit of variation, right? So they're in a bubble, but that bubble has some size, and that variation is determined by heat treatments and specific alloying contents and specific alloying elements, right? And that gives you sort of the remaining 10% of the variation. And if you look at these charts, right, not every part of the chart has a material that has that combination of properties. And so this is mostly due to the fact that, well, maybe that that material hasn't been invented yet. We can't process it to be a useful material. but it's also due just the fact that we have a certain size and shape for our atoms and our molecules, um, and a certain bonding behavior, which limits the properties that we can attain. Okay, so I've talked a lot about the different classes of materials. So what is the process for choosing amongst all of the different materials when you have kind of an open design problem? Um, and Ashby kind of breaks it down into 4 steps, right? You have translate, screen, rank, and then seek supporting information. So in the first step in translation, right, what your goal uh, is to translate the design requirements into um, into property requirements, right? So first you need to consider the function, right? So what is this thing that we're making need to do, right? Is it supporting loads? Is it transferring heat? Um, and then once you've defined that function, you say, okay, so what has already been decided? What are my constraints, right? Does this thing need to be a certain size? Does it need to have a certain shape? Um, what is the environment that it's going to be in, both temperature and, say, corrosion environment. And then within those constraints, right, what are the objectives, right? So, what's the difference between an object or a design that will, be sufficient versus one that will be outstanding, right? So you can say, if you can do the function and under certain constraints, but make it cheaper, lighter, safer, faster, then that would be that would be the objective, right? So the constraints are minimum, function and constraints are both kind of meet the minimum, and then the objectives would be to maximize a particular property. Okay, and then so in the pursuit of maximizing some objective, right, we have some free variables, right? And this is where we have the ability to make a choice and to design something. Um, right, so all of these together help to define the boundary conditions, which enables us to scope our list of prospective materials and to reject large numbers of those 120,000 available materials relatively quickly. Okay, so we have the translation, right? So as we're rejecting materials, the next step would be screening. And so when we're screening, right, this is the ability to quickly reject many materials that are clearly not suitable, right? So we have a list of constraints, and a lot of times those constraints will eliminate materials very quickly. For instance, maximum service temperature, right? So you say, well, this is going to be used at 500 degrees. Well, right away, basically any polymer is out of consideration. And then once you have identified a list of materials that will technically suffice, right, then you're going to rank them in terms of your objective, right? So if you have 10 materials that will work, and you rank them in terms of, say, cost per ounce or something, right? If you're trying to minimize the cost, and that helps you to see which one would potentially be the best choice. And then, at the end of the ranking, you're probably down to a short list. And here's where you really dig into the details to make sure that your material is the right choice. And this allows you to find information on a few materials that would be prohibitive if you were researching, say, hundreds of different materials for these more specific pieces of information. Things like corrosion resistance or availability, environmental impact, right? After you've screened and ranked, right, you're down to a short list that then you can really dig into and make sure that the material that you end up choosing doesn't have any sort of hidden or not immediately apparent drawbacks that would make it unsuitable. Okay, and so let's see here. I have a couple of examples of doing this sort of process for some applications. The first is relatively simple. It's a microprocessor heatsink, right? So microprocessors have current flowing through them that creates heat and degrades the performance, and so you want to get rid of that heat. And so you attach it to a heatsink. What do you make that heatsink out of? Right? Well, in following our methodology, right, we have a relatively simple function, right? It needs to be a heatsink, right? And so that leads to some constraints, right? So we want it to um, absorb heat from the semiconductor device efficiently, and so it needs to be a good insulator, right? Not a thermal insulator, but an electrical insulator, because we want to keep the current flowing in the chip, right, and not drain it away into the heatsink. But it needs to be a high thermal, a high thermal conductivity, right? And so this kind of limits the material choices just in the fact that some classes of materials are characterized by high electrical and thermal conductivity, but here we just want one or the other. And so, right, so we have a minimum value for electrical resistivity, and what we want to do is maximize the thermal conductivity, right? So we have a minimum resistivity necessary to isolate the semiconductor device, and then within that we want to just have the highest thermal conductivity that we can to make the best heatsink and to pull away as much heat as possible. So within those constraints and looking to that objective, right, we have some freedom, right, and that freedom would be the choice of material. And so the chart that we want for this problem contains the two properties that we are interested in, right? That would be resistivity and conductivity. And so we pull that chart here, right? And so we see that for resistivity, we know that we want to have a value, right? Our constraint says the resistivity has to be greater than 10 to the 9th microohms per centimeter, or microohm centimeters, right? That's right here, right? So you can draw a line at that resistivity, and basically anything below that is not considered, right? And then you would say, okay, so we want to maximize the thermal conductivity. Well, that is on the y-axis, and so on the right side of the chart, we see that we have a grouping of materials that would technically be suitable, but have a relatively low thermal conductivity. And so right away, we identify this upper right quadrant that has a low enough or a high enough electrical resistivity and a much higher thermal conductivity, right? Especially since most of these charts are log-log, right? This much separation, we're talking, orders of magnitude difference in thermal conductivity. And so we see that heat sinks, we're going to want to choose, right, these semiconductor materials, or these, right? So we have alumina, we have aluminum nitride, silicon nitride. Those are our heatsink materials of choice. All right, so that was example number one. That was kind of simple. If you have a more complex example, which we'll talk about here in a minute for springs, performance is more complicated, right? And if we kind of break it down into a function, we say, okay, so P here is performance, and performance has a couple of components that go into it, right? First of all is the functional requirement. So if a material, depending on what it has to do, will depend upon what we consider its performance to be. And also its geometric parameters, right? How is it shaped? That factors into its ultimate performance. And then the material properties. And so if you can define a function that describes the performance for a particular application, then you may be able to determine which factors will maximize P most effectively. And it's helpful from a material selection standpoint to be able to separate the functional forms for the requirements and the geometry and then the material properties, right? Because if I can isolate only the material properties, then that allows me to kind of zero in on a particular chart and make a good material selection and not consider the functional or the geometry as heavily because I have separated, I've kind of isolated that, um, and for a given geometry and a given function, I'm going to have the same contribution from those factors, and I can just look at the contribution due to the material selection. And so this can be very helpful. So if we look at an example for a spring, right, deriving an expression, we can start with Hooke's law, right? So that would be the force from a spring is opposite in direction to the displacement and proportional to some constant. And so if we integrate force, we get work that has this functional form here. And so if we think about, right, a spring is elastic deformation, right? You push on it, it compresses, or you pull on it and it expands, and then you can go back and forth, right? That sounds a lot like the elastic region of a stress-strain curve, right, which we can define in terms of stress and strain. It gives us the elastic modulus, right? So when we think about displacement of a spring, that's analogous to the strain on a stress-strain curve, right? So our x in Hooke's law is really the epsilon, the strain, as we stretch or compress a material, which allows us to make a substitution. So sigma over x is our epsilon, or is our Young's modulus. So we can solve for x in terms of stress and Young's modulus. If we sub that into our value for x from our expression here for work, right, then we can get an expression for work, which is our performance variable, right? So we want to maximize the amount of work done by a spring, right? The amount of energy that it can store is 1/2 sigma squared over the Young's modulus. And so here, this is a relatively simple example, right? We have our functional and geometry requirements kind of buried in this 1/2 parameter. And so if we look up here, that parameter in the simplified example varies depending upon the geometry of our spring, right? So if we have a more traditional spring, right, that's kind of what we derived below, but you could also have it's like a beam, which is like a leaf spring kind of, or a torsion device or design, right? In which case the functional form where the geometry and information is stored has changed. So what we wanted was to isolate the material properties, which we have here, and sigma squared over epsilon. And so to make the best spring possible, what we want to do is maximize this value here. So we have, say, M1, which is our performance material variables, and we could also secondarily look at them on a specific basis where we would just divide by the density. Okay, zoom back out here. Right, so for this spring example, trying to zoom, the chart that we need is Young's modulus versus strength, right? That's what we have, right? We have the yield strength divided by Young's modulus. So our performance variable is this M1, right? Sigma y, yield strength squared over the Young's modulus. I always, these are typically plotted on a log-log basis, so if I take the log of both sides, I can rearrange into a point slope form where I have y equals mx plus b. And the slope is 2, right? That is from my exponent here. So if I have this combination, right, so for springs, the slope is always going to be 2. And the y-intercept, right, is dependent upon the combination of yield strength and modulus, right? So for spring applications, right, I'm always going to have slope 2, but depending upon the combination of properties, I will take this line and translate it left or right. And any point along that line will have the same value for m sub 1, right? So for instance, this line that's drawn on here, right, is for an m value of 2 times 10 to the 6th. Now I can get that by choosing, say, metal properties, right? So that would be a strength of, say, 200 megapascals, a Young's modulus of, say, 20 gigapascals, right? If I plug that in, right, I get an m value, 2 times 10 to the 6th. Right? I could also pick a line down here in the polymer region, right, where I have a Young's modulus, or a strength of, say, 20 megapascals, and a Young's modulus of only 0.2 gigapascals, right? But if I plug that in, I get the same M1, right? Which it would indicate that I could make this a spring with equivalent properties, at least on a strength and modulus basis, of a polymer or a metal, right? Because I have the same performance value. On a specific basis, right, I have the same thing, except I have divided by the density. And so my line here is of a similar form. But based on the density, right, my materials are going to shift around slightly in where they fall on that line. But for the spring example, right, if I'm looking at sigma squared over E, right, the yield strength over the Young's modulus, and I look at different classes of materials here, I see why most springs are made out of spring steel, in the sense that I have this performance variable among titanium and carbon fiber. From a just efficiency standpoint, spring steel doesn't do too bad, right? And it's pretty available. It's easy to work with. It's easy to heat treat, and so that's why it's the dominant material. But interestingly enough, if you look at polymers and elastomers, right, you can actually get a higher performance, at least on the basis of yield strength and modulus, out of a rubber spring, right? Right, and these are, you know, probably even cheaper than spring steel. The problem here, and this isn't captured on our chart above, is the high loss factor, right? So it can store, you know, the same amount of energy. Well, it's an equivalent spring on the basis of yield strength and modulus, right? But it's not good for storing energy because of the high loss factor. So this is an example where my methodology can get me down to a short list, right? And then I dig into the other factors, right? And that might eliminate some otherwise promising candidates. We see here that the case for rubber actually gets even stronger when you look at a light spring, right? So here we're factoring in the density also. And for light springs, right, steel actually doesn't do too well because of the high density, right? So I can get an equivalent or better performance, right, from, say, a carbon fiber spring or a fiberglass spring material or titanium because of their lower density. Again, rubber kicks butt here totally, but you would disqualify it because of the high loss factor. Okay, so this is running a bit long. This is kind of 2 lessons in one, so I guess that's maybe okay. The last example I have is for a beam, right? So we're looking for a stiff, light beam. This is a very common application for, say, floor joists or wing spars. Here we're looking at just a rectangular cross-section, so you can certainly have more exotic geometries, but here we're just trying to keep it simple to illustrate a point. And so our design methodology here, again, our function is a beam, right? It's going to hold a load. And then the constraints, typically the size of the beam has been dictated, right? The size of the part has been given to us. So L is specified, and also the load that needs to be supported has been specified, as well as how much deformation, deflection is allowed, right? So that defines the load and the stiffness of the beam, right? So these are things that we can't change, and our objective, since we're making a light stiff beam, is to minimize the mass. Right, so when we're minimizing the mass, you can already think, well, I'm probably going to be picking one that has specific properties, right? And to do that, right, we can change the cross-sectional area, right? So that's a modification of a geometry parameter. And we can choose a particular material. And so since, right, so our methodology, what we want is to define this performance variable, right? Our performance variable, our objective, is mass, right? So we want to have a function that gives us mass and allows us to isolate the material properties, right, ideally. And so our constraint is stiffness, right? We have a specified stiffness. And so a functional form for that is, so stiffness is load divided by deflection. So you have a high stiffness if you have high loads and low deflections. And we're saying here that we have a minimum value for this. So the stiffness must be greater, right, than this expression here, right? C1, which is a load distribution constant depending on how the load is distributed throughout the beam. And then that's multiplied by Young's modulus. Right here we have a material parameter popping up. The second moment, which is related to the geometry of the beam, the width and height, and then the length, right? So that's a fixed variable. So here we can kind of do some geometry. So stiffness is our constraint. So we have a stiffness that's got to be greater than or equal to this variable here. We've substituted the second moment for our horizontal geometry, and here's where if we had, say, an I-beam, this would just be a different value. But here we have a rectangular cross section, actually a square cross section, right? So it simplifies to a squared. The cross-sectional area squared divided by 12. Since we have different, size and shapes of beams, it would sure be nice if we could eliminate A as a variable. And so if we have the density, we can do that, right? Density is just mass per volume. Volume would be the area cross-section times the length. So we can rearrange this in terms of A squared being in terms of the mass, the density, and the length. So we'll make that substitution here and simplify a bit. And then what we want to do is to start to gather up and rearrange to isolate our objective variable, right? Our objective variable is the mass, right? Because we want to have the required stiffness with as low a mass as possible. So ideally what we want to do is solve for mass and then separate into our functional geometry and material properties components of our function, right? So we're going to start to try to do that. We're isolating the mass here, and then we're gathering up our functional, our geometric, and our material properties. So this is more complex than the previous examples. Remember, for the spring, it was just 1/2, 1/3, or 1/4. Here we have functional components that are related to the load distribution and the length of span and the stiffness of the beam, right? So we've kind of gathered those all up together. Those we can't really change. And then we have this geometry, which we have L over here, but L cubed. So the length here is more important, and we could potentially have the area in here, but remember we already made that substitution to eliminate the area variable. And then we have a couple of material properties, right? So we added in mass when we got rid of the area, and we had Young's modulus from the very beginning. And after that algebra, we see that we have the density divided by the square root of the modulus, right? This is what we want to minimize our result in M, right? Or conversely, we could try to maximize the inverse of this, right? Which would be the square root of E over delta. Which leads us to the chart we need, right? Well, the chart we need is Young's modulus and density, right? So we'll pull that chart and plot a line through that is related to our combination of variables here. We have a different line for different exponent on the Young's modulus, right? And here if we rearrange this function, we have, right, take the log of both sides, bring down our half, rearrange into a point slope form, we see that, right? A log of E is our y-axis, log of density is our x-axis, and then our slope is 2, related to our exponent, and our intercept is at C, which is indicative of sort of our optimization variable. So meaning that for this application, right, we will have for different values of C a family of curves with the same slope, right? And so as we move up and to the left, right, we're getting better combinations of properties that increase this C and decrease the mass, so that would be desirable, right? As we move down and to the right, we're getting heavier, lower moduli, and so those would be worse for optimizing our particular design here. Right, and so we see that for our beam, right, for a light, stiff beam, you know, the metals are actually disadvantaged, right, and so we see composites, right, there are some composites that we would predict would fall into our acceptable range, and then actually, interestingly enough, right, we would have maybe some wood that would fall into that category as well. Now, for wood, we would probably have a larger cross-section, but remember, every point on this line has an equivalent value for C, right? So, and that's enough to kind of put both composites and wood on our short list, in which case we would start researching things like cost and availability and lifetime and those sorts of things to choose between a much shorter list of materials. So hopefully, and I'm sorry this went a bit long, but again, this is kind of meant to be 2 videos, so you can watch it, you know, in 2 parts if you'd like. But I guess I said that at the end of the video, so you've probably already watched it. Anyway, the point here was to multi-fold, right? To review some of the material properties that we've talked about for the first half of the quarter. Also to lay out this systematic approach for choosing amongst all the many thousands of available materials for a particular application.